Good morning and welcome to EE252 Electronic Devices and Circuits. Today we are going to continue on feedback amplifiers, and today this section will be concluded, and from the next class uh, the section on FET will be started by Dr. KRM Ratnayaka. I'm not sure whether he's planning to do it online synchronous mode or recorded lectures. He will contact you regarding that. Uh, right, before we actually get started, there was one question from Senara. I'll start with that. And if you guys also have questions, you can ask before I actually get into the actual lecture. Okay, so let me share my screen. Right, the question Senara had was basically I have a doubt on feedback amplifier topologies. My concern is how we can take the feedback input impedance, as you mentioned in the lecture, in series shunt and series. Okay, so basically this is something that we covered, but let me go over it again for series shunt as well as series. Okay, so right, you guys can see my screen.
Yes, sir, we can see.
Thanks.
Excuse me, sir, we can't hear you.
Thank you. Let me see.
Hello.
Hello. Can you hear now?
Yes, sir, now we can.
Hello. You guys can hear me now, right? Hello. You guys can hear me now?
Yes, sir, now we can.
Okay. All right. So please let me know if the sound goes on. Okay. Because my microphone keeps detaching. That is the issue. All right, so this is the circuit. So we have the output like the output has a voltage source for this. So this is my circuit without feedback. Okay, so this is the amplifier, voltage amplifier without that is a series shunt connection. Now you know the definition of RI with feedback is basically if you input a voltage, it draws a current IS, which we call this I in. So that is I in. We need to find this when the output is not loaded, unloaded, right? Unloaded. In this case, unloading means no current flowing, right? So therefore, I out has to be 0 in this case, unloaded condition. So therefore, Vs we can write as, so since I out is 0, V out should be equal to AV times Vi. Okay, because output is 0 by definition. This is the definition. So, but Vs we can say is equal to Vf plus Vi. Right. So this voltage plus this voltage is equal to that voltage. Okay, so that's basically here. And we know Vf is defined as the ratio between, so the feedback factor beta is equal to Vf over V out. So therefore, from this we can write Vf as beta times V out, but we know V out is equal to AV times Vi. This gives me Vf as beta AV times Vi. Okay, so therefore I can write this Vs as Vi plus Vf, which is equal to Vi times 1 plus beta AV. Similarly, I is I times Ri is equal to Vi, right? So I times Ri is equal to Vi. So therefore, I'm going to substitute Vi with that. So Vs is equal to Ri 1 plus beta AV. So therefore, my definition Vs over Is equal to Ri times 1 plus beta AV. Is this clear? So this is how you prove the input impedance with feedback for series shunt topology. Senara, is this clear?
Yes, sir. It is clear, sir. Thank you.
All right. Wait, the only difference when you have the series connection is instead of this right here, what you will have is inside the box input will be a voltage, but output will be a current, right? Output will be a current. It will be like that. Input will be just like this. Input side, there is nothing changing, but output will be like that. So the current I out. So this will be V in times GM, right? It's the output current, and this will be the output current. This is the source current of the output, and this will be the R out. But in this case, you have the feedback circuit just like the before. Sorry, yes, no. Like that. So this will be my Vf in this direction. This is Vi. So this is my Vs.
right? So this side is the same. The only difference is in this case I define RIF as again VS divided by II, where this is my II. Okay, so input impedance looking into this term, right? RIF. But in this case, I have to use output no load. No load means I do not connect a resistor, so this has to be short circuited. So I out totally flows through this. Okay, so therefore I out totally flows through this means V out has to be 0. Okay, that is the difference in series connection. It is not loaded, unloaded condition. So therefore everything else will be the same, except that now VF will be equal to beta times I out, right? I out will be equal to GM times VI, VF, right? So this is the only difference. So at the end, you will have RIF equal to VS. VS again, similar to this, I will have RI 1 plus beta GM. Okay, this is the only difference that you will have in this case, right? So this is the only difference that we will have in this case. Therefore, RIF by definition, so this is VF, no, sorry, VS. Okay, RIF will be equal to RI 1 plus beta GM. So the gain instead of AB, now you have GM. That is the only difference. Is it clear, Senara, for the series?
Yes, sir, it's clear, sir. Thank you.
So there may have been other people who might have had the same question, so you might get the answer here, right? Good. All right, let's now any other questions you have? You guys have any other questions? Okay, so no other questions. So to wind things up, let me now summarize things. Before summarizing, let's have a look at.
Excuse me, sir.
Yes.
Again, we have difficulties hearing you, sir.
Okay. This problem is with this microphone. It keeps popping out. Okay. Now you can hear, right?
Yes,
Hello?
sir.
Yes. So I'll give you some examples, okay? Of feedback circuits, right? For each of these different types, okay? So the first type we have already seen voltage series feedback. Oh, series shunt. This is basically what we have analyzed actually, the voltage amplifier with feedback. Okay, so what you have here, we looked at one circuit. Now I'm going to give you two-stage circuit, right? You know, it's a little bit more complicated. This is just an example. You don't have to memorize this or anything. I'm just giving you just to give you some idea about different types of circuits. Okay, so in this case, let's so this is a two-stage circuit. You have the first stage. Let me have a bypass capacitor, this, right? And let me have this is the biasing circuit. This powered. and this is the voltage into a capacitor. Now, this is connected to a second stage using RC coupling.
Excuse me, sir.
You can't hear, no?
We can't hear you clearly.
Okay, hold on. My microphone. Is it better now? Hello?
It's better now, sir.
You can hear, no?
Now, yes, sir.
Okay, good, thanks. So here, let's have the second stage again, because this is RC circuit, you should have a second set of biasing resistors. So this is the biasing circuit for the second stage, and then you have the amplifier again, something like this, the bypass capacitor, right? And this is my load, so basically this is my RC, and output is a voltage from here. This is my output. Let me. This is my output circuit. Now, how I'm going to get the feedback? Now, since I need the shunt feedback, I'm going to sample the output and the input. So therefore, let me mark it like this and connect it to this point. Okay, so that is my this is the okay, have even basically here, so that it is only for the AC feedback, right? As you see, this is a again a different kind of voltage series feedback. Earlier, remember, if you take the first stage itself, it has voltage series feedback. We have the resistor here that acts as a feedback circuit for the first stage as well. But in addition to that, we are going to provide from the total output. Okay? So output here is the voltage. This is the total output, V out, and my input is provided from here, Vs. So this is the input, this is the output. Okay, so that is my sample circuit. The beta value you can show is equal to Vf. This is Vf over V out. Right? Typically, how do you do it? You draw the circuit without feedback. I'm not going to do it for this circuit because it is a little bit more complicated, but you can, because you have the first stage also with feedback. I'm not going to draw the equivalent circuit there, the simplified circuit there, but this will be R1 plus R2, where R1 plus R2 are, this is R2 and this is R1. Okay, so that will be your circuit. Now, if I give you some typical values, say for example, let me make this 50K, 47K, 10K, 47K, and this one is 100 volts. Okay, 47K. This one is 33K, 4.7K, and this one 4.7K. RL 4.7K. So like that. Okay. So you may have capacitor values in the range of tens of microfarads, 10 microfarad, 50 microfarad, 50 microfarad. Okay, so this is 25 microfarad, 5 microfarad, right? So at depending on the resistor values. RC value will be in that order. So not just C value, you have to look at RC. That is what defines the cutoff frequency. Okay, so it will be like that. So that's an example circuit of series shunt feedback. Okay, now the second circuit that I'm going to give you is the current series. Okay. Current series feedback. Current series. What do you mean current series? Series. Okay. So the output is a current. Input is a voltage. Okay. So an example would be an emitter follower. So just like what you had in the example, you have an emitter follower. Hello? Still not hearing? You can hear, right? Hello? You guys can hear?
Sound is not clear.
Yes, sir. It's like fluctuating. So sometimes we can hear you, but sometimes we can.
Okay. We'll try to manage. Is it now better? At this point? Let me see what I can do.
Now it's somewhat clear, sir.
Somewhat clear. Somewhat. It's not good. I want it to be good. Okay, how about now?
Now it's clear, sir. Right?
Now it's clear. Huh?
Yes. Yeah.
Please let me know when if it goes bad. Okay, I'll try to adjust it again. So this is voltage follows. Therefore, this is what you have. So you have input is a voltage source. So resistor. So this is VS. This is VS, and you take the output here. The output in this case is a current. Okay, this is plus VCC. Let me call this RL. So this is the load itself. Okay, so this is RE. This is, let me call RS. Okay, so in this case, my output actually I'm going to mark it like this because typically when you look at a circuit, we mark the input output. If it is a voltage, it is like this. And currents, we mark input current and output current, right? So therefore, that is the reason I am putting I out like that, but I out actually may be negative, right? In this case, the value of I out may be negative, but I'm going to put it like that with this, with this convention, right? Output current going out from the circuit. Okay, so this is my I out, that is the output, and this is my input. Yes, that's my input. Okay, so in this case, you will see that the since this is an input, RF, so the VF will be across this. Okay, across this will have the VF. So what you will have this is beta value. You know, let me first draw just to practice. Okay, let's draw this without feedback. Let's draw this without feedback. If you can remember, in order to find the input circuit, what you do is if you have voltage sampling is what you have. If you have voltage sampling, you set the output voltage to 0. If you have current sampling, you make the current output to 0. Now, in this case, what do we have? We have output is a current, right? So output is a current. So therefore, what we have is a current sampling. So therefore, we set the current to 0. I open circuit, this RL. So therefore, I out will be 0. if I out is 0, what will be the value of VF? VF will be 0, right? There will be no RE. There will be no current here. Therefore, my input circuit will be without RE. So the input circuit will be something like this. Okay, so this will be my input side, and then since it's a voltage source, I'm going to replace my. I don't have to do anything. It is already the voltage of Thevenin, right? So that is basically the input side. The output side, what do we do? Output side, to find the output circuit, set the input voltage to 0 for shunt comparison. Shunt comparison means you connect to current. Feedback is current. In this case, that is not what we have. Or else input current is made to 0 for series comparison. Right? So this is basically what you have. We connect the feedback in series. Right? This is the voltage. So therefore, input current will be made 0. So therefore, the current that I have in this branch, I will be 0. If there is no current in that branch, the total current flowing through RA will be I out. So therefore, what I will have is between resistor and emitter, I will have two resistors, RL and RE. And what is the output? This is my out, I out. And what is the VF? Again, VF is the voltage across this, but in this case, it's in that direction. In that direction, I have that. So this is my VF. Okay. So what I will have is a negative value is beta will be equal to VF over I out. VF over I out. VF over I out. So we can write this equation. VF is equal to minus I out RE, right? So therefore, this is my beta. Beta will be equal to minus I out RE divided by I out. So beta will be minus I out. Sorry, minus RE will be my beta. It's constant, right? And what is the gain? Gain will be in this case GM. Okay, GM is equal to output voltage divided by output current divided by input voltage, right? So that will be equal to I out divided by VS, right? So VI input to the circuit. So this will be that. Okay, so this is my VS and that is my out. So and this is my VF. Okay, hope this is clear how to obtain these values. So once you have beta and A, you can find any quantity with feedback. With feedback, the gain will be reduced to GM divided by 1 plus beta GM, right? Likewise, you can find the other. Is it clear? All right, so that's a current series. So series feedback. The third one that I'm going to show you is called current shunt feedback. Current shunt or shunt series. So this one is what current series is transconductor, right? Amplifier. This is a voltage amplifier. So the third one we are going to have is a current shunt. So the shunt feedback, what you have is a current amplifier. Okay? Input and output are current amplifier. So now I am going to do it like this. Okay? So I will have the transistor like that. I'm going to do a two-stage transistor amplifier, and second stage taken from here, and you'll have emitter resistor as the load. This is the load. Okay? This one is the load resistor. So that is my load plus VCC here. And I'm going to mark this as a volt input as a I'm connecting a voltage source to this is a current amplifier, right? So my input I'm going to mark as a VS, but my input to this circuit that I'm considering is going to be I want to amplify this into IR. Okay. Now this is as if you have a Thevenin's equivalent circuit representation. If you have a current amplifier, you need to convert this into a current source. Okay. Remember, it will be represented as current source. So VS divided by RS will be your current, but if it is given as IS, that is fine. Okay. So this RS is the source of the Thevenin's equivalent circuit. Okay. So in this case, what do we have? We need to put the feedback. The feedback I'm going to put. It's a. I'm going to. The output is current. Therefore, it has to be taken in series, right? And then, since input is current, it has to be subtracted in shunt in parallel, right? So therefore, I need to take some current from here, so that IS minus IS will be the I in, okay? And this will be connected. Okay, that is my R dash is my feedback resistor. Now, in order to find the beta value, how do you find it? Okay, we need to figure out how to find the beta value. But we know beta value, beta can be written as IF over I out. Okay, what is I out? We know the current to that side. But what is IF? How do you find that? Right? Now, in order to do that, first let's simplify this circuit by using the principles that we learned. In order to obtain the input circuit, what do we do? So first, we replace the current source, the voltage source with the current source, right? So therefore, let me initially do that. That's my IS. And then I have the RS. Now, in this case, this will be infinity because the voltage source input impedance, output impedance was 0. Of the voltage source, okay? So this was equal to 0. So therefore, this one is infinity. So what we have, what is given is IS, right? So therefore, IS is already there. This is RS, and in order to find the input circuit, what do we do? To find the input circuit, set output voltage to 0 voltage sampling, which is not the case in our case, or else set the output current to 0 for current sampling. So this is exactly what we are going to do. So I'm going to make this equal to 0. If I make this to 0, there will be no current flowing through this. Okay. If there is no current flowing through this, the total current IF will be flowing through that, right? So therefore, what you have here is R dash and RE in series. Okay? R dash RE in series. So that's my input circuit. Then I have my transistor here, first transistor connected here, and then I have the collector resistor 1, R1, RC1, that is between this and the ground, again, like that. And the output of that is given to the second transistor. Now I need to find the output circuit, right? Output circuit. How do I find the output circuit? To find the output circuit, set the input voltage for shunt comparison, right? This is a shunt comparison because the current feedback is a current, so therefore that is exactly what we should do. Input voltage has to be 0. That means you are short circuiting this and that. So when you short circuit this, input current will be 0, right? Input current will be 0. There will be no current flowing through that. So the total current that flows through this circuit, this resistor RE, will be output current. Okay, so therefore the current output current will be flowing through my RE. This is RL. This is RL. Okay, that's my RL. So this is my circuit. Mind you, I am not connecting these two places, right? These two places are not connected. I'm not connecting these two. It is irrelevant. So this is for the output circuit. This is for the input circuit. What is my input signal? IS. That's this one. And since this is there, so that will be my IS. Okay. And what is my output? My output will be, again, this is my I out. So therefore, I out will be flowing through this. So this will be the output voltage. And this will be my VF. Okay, so VF will be like that. But now I R in addition to R in. So now what did I do? I short circuited this, right? Remember, I short circuited this. So what do we have in the output? I have this resistor in parallel with this path, right? So therefore, in that path, what do we have? I have, in addition to this, I have another path. I have another path that is R dash. So R dash will be in this also. So this is not the VF, I'm sorry. So VF is there, right? VF, all right. So this is VF, but feedback signal is not a V, it's a current. So current will be R dash. So this is my IF. Okay. IF is that. So how do I find the IF? The IF will be divided between the current resistors based on their resistance, right? So I can say IF times R dash. IF times R dash is the VF, is equal to the total current. I can mark it as I out times R dash parallel RP. Okay, so this is the total voltage flowing through the parallel combination of these two will be equivalent to RF, right? So therefore, IF beta value will be equal to IF over I out, which is equal to R dash parallel RE divided by R dash, right? You can simplify this, R dash RE over R dash plus RE divided by R dash. Okay, so get this out. The beta will be equal to RE over R dash plus R. So that is my feedback. Okay, so the beta is equal to RE over R dash plus RE. Let's we obtain that. And A, in this case, A is equal to I is equal to I out over IS. So this is the without feedback. So once you have both these values, this is basically, this is the one that we already have access to for this circuit. This is the current gain of this circuit. And if you have these two quantities, you can obtain the current gain with feedback, the input impedance with feedback, and output impedance with feedback. All these things we can find. Okay? So this is the current shunt feedback mechanism. The third one, you guys still can hear me well, right? Hello? You guys can still hear me well, right? Hello?
We can hear you, sir, but there are some
But
up and downs.
yeah,
I'm really sorry about this problem that I have with this microphone. We'll try this. Okay, the last one that we are going to look at is the shunt or voltage shunt feedback. Voltage shunt or shunt feedback. We use this for trans resistance amplifiers. For the trans resistance amplifiers. So let me give you an example circuit. You have something like this, and you connect again source. In this case, I'm putting it as base, but remember, trans resistance input is a current, right? So what I'm actually amplifying is the current. So it's a voltage source, and my feedback circuit basically is something like this. This is my feedback. RC R dash RS, and I'm sorry, there is like that. Okay, so this is my trans resistance amplifier. Here, output is a voltage, so therefore output is taken from here. V out, but input is a current. I okay, so it's marked as IS source current, right? So if you want to draw the equivalent circuit, or basically circuit without feedback, you have to follow the same principles that we talked about earlier, right? What are the principles? In order to obtain the input circuit, set the V out equal to 0 for voltage sampling, and set I out equal to 0 for current sampling. This is a voltage sampling. Output is a voltage, so we sample using voltage sampling. So therefore, V out is made to 0, right? So therefore, what we have to do is we have to short circuit this and this. So as soon as you short circuit this, what you will have is basically at the input you have this in parallel with that, right? They will be in parallel. So my input circuit will be, I have two resistors in parallel, R dash and R is in parallel. Obviously, you can replace your source with its Norton's equivalent circuit like that. Okay, so this is my IS. IS is like that. And you have the transistor. Now, To find the output circuit, set the input voltage to 0 for shunt comparison, right? That is exactly what we should do. If it was for series comparison, that is, if you were adding a voltage, subtracting a voltage, I in would be made to 0. But now, since we are using a shunt comparison, we need to set VI to 0, input voltage to 0. So that means you are short circuiting this, right? This is short circuit.
Excuse me, sir.
Yes.
Again, we couldn't hear you.
Okay, I'll say that again. Okay, let's try with the. How about now? Is it better now? See.
Yes, sir. Now it's
It is,
much better.
without an external microphone. This is internal microphone. Is it better?
Yes, sir. Much better.
Not yet.
Much better now.
Hello.
It's good, sir. It's way better than that.
Yes, sir.
Hello. Hello.
We can hear, sir.
We can. Yes, sir.
Okay. Hold my mic. Okay, so find output circuit. What we do is basically short circuit the input. So Vi is set to 0. That means it is like that. So once you have that connection, so in order to find the output impedance, you have output circuit. You short circuit this. When you short circuit this, there is no current going into the amplifier because the whole current will be short circuited through this shunt, right? So therefore there is no input current. So therefore there will be no output. So the whole output will be divided between the RDS. The collector will be between the emitter and the resistor. Emitter and will be like this. So the resistor will be connected like that. That will be my RC, which is already there. So we connected to ground in the AC circuit. And in addition, we will also have between collector and ground, because this point is now grounded, right, to RS. So this will be connected. Let me see. Input is 0. Input to this is 0. Therefore, okay. So R dash and RS as because you have between this and that you have like that. Okay, so between the ground and the collector, you have these two resistors. In my note, I have just R dash. That is why I was looking at it, but I think this is correct. So you have the output. It's a voltage. So this is the output voltage, and this is my input current. Right. So therefore, what is the beta? Is the VF over V VF over V out. Let me double check. I have drawn this right. Okay, all right. This is correct. So what we need is input is a current, right? And the feedback signal is a current. So therefore, the current signal is this. This is the IF. This is I out. This is IF. Like that. So therefore, output is a voltage, but my output is a voltage, but my feedback signal is IF. What we need is beta is equal to IF divided by V out. Correct? Right. So this therefore this should be equal to so this should be in the direction has to be So value wise, this will be equal to 1 over R dash plus R S. Okay, because we have V out is equal to IF times R dash plus RS. Therefore, my feedback signal is that. Let me see if I have marked the voltages in the correct direction. Okay. So current will be in that direction, right? So the current is towards the collector. So therefore, I need to mark this as IF as this. So therefore, it will be negative of that. So therefore, my value will be minus beta. So therefore, beta value will be 1 over R dash RA plus RS. Typically, RS is much smaller than R dash. R dash will be in kilo ohms, several kilo ohms, tens of kilo ohms, and RS will be in tens of ohms or something. So therefore, typically this will be approximately equal to 1 minus 1 over R dash. Okay, so this is basically the beta value. And similarly, A, the gain without feedback will be equal to Rm, which is V out divided by Is. This is the value. V out is okay. So once you have beta and A, you can find all the other quantities. Okay. So this value will be roughly equal to 1 over R dash when Rs is much less than R dash. Okay. Hopefully this is clear enough. Any questions so far? Any questions? I think we have basically covered everything that we have to cover, and except that I will summarize this quantities. Any questions so far, guys? Okay, no questions. Good. Let me then summarize this in a table. Okay. For each of these amplifiers, voltage amplifiers, transconductance amplifier, current amplifier, and transresistance amplifier, which are also known as the feedback topologies, are known as voltage series, current shunt, and voltage shunt. Or in another way, these other names also. The feedback signal in the voltage amplifier should be a voltage, right? Should be a voltage. Feedback is a voltage, and output is also a voltage, right? And obviously, transconductance amplifier, the output is a voltage, but the input is a current. Likewise, current amplifier, both are currents, input and output. And the resistance amplifier, input is a current, but output is a voltage. Okay, like we know. Now, this is the important thing. To find the input circuit, what do we do? Right? If it's a voltage amplifier, to find the input voltage, since output is a voltage, we set the output to 0. V out is equal to 0. We set V out to 0. To find the output circuit, I open circuit the input, right? So therefore, I in is equal to 0. Okay, so input is open circuited, output is short. For the voltage amplifier. Similarly, for the current series amplifier, output again is a current, output is current, so therefore you need to set the output to 0, so I out is equal to 0. And input is a voltage, therefore again our voltage is open, input is open circuit, so therefore this will be equal to 0 also. And similarly, you can figure out the other ones depending on the output. Since the output is a current, you set output to 0 for current amplifier. Since this is a voltage, input is a current, we set the voltage to 0. That means you short circuit. Okay, we short circuit the input. we short circuit the input. Okay, and voltage shunt transconductance amplifier output is a voltage, so therefore we set the voltage to 0. Input is a current, so we short circuit the input. Okay, Vi is equal to 0. So this is important, and the feedback signal in this has to be represented as a, since it is a current, a voltage, it has to be represented as a Thevenin equivalent circuit. Okay, Thevenin circuit, the value, the beta value will be VF or V. And again, again my feedback signal is a voltage, so therefore it has to be represented as a Thevenin equivalent. And now the beta will be equal to V feedback divided by output value, which is I out. Okay, for the other two, there will be Norton's equivalent circuits because the input is a current, right? This feedback signal has to be represented as a current. Both these. Okay, and beta value we have to obtain for the current amplifier as a ratio of currents I divided by I out for the current amplifier, and for the trans resistance amplifier it has to be feed, the input is a current but output is a voltage, so therefore like that. Okay, and the gain without feedback, right? Output voltage divided by input output quantity divided by input quantity, right? So since this is a AV voltage amplifier, we have a voltage gain which is V out over VA, and D, right? The loop gain will be 1 plus beta AV loop gain. GM will be the gain for the transconductance amplifier. It has to be a transconductance GM. So it will be I out over, this is the output, input is a voltage. Okay, and again 1 plus beta GM is the gain, will be the loop gain. And for the current gains, it will be a current amplifier. So therefore current gain is equal to I out over I in, or I suppose 1 plus beta AI will be the loop gain. For the trans resistance amplifier, the gain will be a resistance as units will be equal to output voltage divided by input current, and the D or the loop gain will be equal to 1 plus beta RM. Okay, so these are the equations, and knowing these things, we can easily find the quantities with feedback. A voltage gain with feedback will be equal to AV divided by 1 plus beta AV, or D. Okay, input impedance will be increased, right? So therefore Ri times D. Output impedance will be decreased, so therefore this will be R out divided by D. Okay, so this is how the voltage amplifier will behave. With feedback, it will reduce the gain, it will increase the input impedance and reduce the output impedance. For the transconductance amplifier, the with feedback, the gain will be reduced. Obviously, all the values will be reduced with gain, right? With feedback. So Martin also divided by D. Whereas the input impedance, again, this is a input is a voltage, so therefore it will be increased. So you are connecting something in series. When you connect something in series, impedance has to increase, right? So, and the other two cases, you are connecting a shunt or parallel connection because you need to feedback the current, so they will be reduced. The input will be input resistance will be reduced. So both these cases, Ri will be reduced. Okay. output impedance, in the case of output is current, when you add something in series, the sampling network in series, output will be increased. So therefore, R out will be R out times T. Okay, and here again, output is a current, so therefore output impedance will increase by a factor of T. And for the trans resistance, output is a voltage, so therefore it will be reduced. Okay, so this is basically the summary of what we learned in this feedback amplifier section. Right, all you need to do is apply these things to find the circuit without feedback. Right, so we used the example in detail, as well as when we looked at the last 3 or 4 examples and example circuits, we figured out how to do this. Right, if you can't do it, you have to practice. Right, see, what do you mean? This is step number 2 is what is important. In the example I gave you, step number 2, where you replace the circuit with feedback by circuit without feedback, right, by following the steps. So what you need to do is you apply the steps. You apply the steps and obtain the circuit without feedback. Okay, so to find the input circuit, remember, output has to be made to 0. So output made to 0 means if the output is a voltage, you make the output voltage 0 by short circuiting the output. If the current is the output, in order to make the load 0, what you do is open circuit the output. Okay, so and this is basically what you do in this case. And to find the output circuit, if you have a voltage as an input or the feedback signal, not that type, the other one is made to 0. In other words, you if the voltage is input, current has to be 0. That means you open circuit the source. Open circuit means you don't provide any energy to the circuit, right? So that's basically you do that and find the output circuit. If the input is a current, then you open circuit the short circuit the input, so that the whole current is shunted through that short circuit. Nothing is given into the circuit, right? And then you find, so that there is no energy provided by the source, you can find output just looking at the circuit that you have. Okay, so that is what you do. Okay, so that brings an end to this section on feedback amplifiers, along with the section on BJT. Right, I have made available one tutorial that is due today. I hope you will submit it. Remember, I am not going to grade it. I am going to give grades. I'm going to give marks to everyone who submitted it. So therefore, please make sure that you submit it. And what is important is that you try it on your own first. If you can't do it, you talk with your colleagues, understand how to do it, and then try to do it on your own. Even if the answer is wrong, don't worry, because I'm not going to grade it. Whoever submits it will get grades, right? The marks. What matters is that you understand it, so that when if I give a similar question in the exam paper, you'll be able to do it. Okay, so that is the objective. So don't try to copy from someone. It doesn't matter whether you copy and submit, or just do whatever you want the wrong way and submit. You will get the same number of points. Right? So therefore, no point in copying, but try to understand. I will also make available a second tutorial soon, and I will make available the answers to the first tutorial also. Okay. Any questions, guys? Because after this we'll not have classes conducted by me for some time. Unless you want me to, you can make a request. I can arrange one. So therefore, you have to let me know any questions now. remember in the final exam, half of the marks will be allocated from the sections that I covered, right? BJT and feedback amplifiers. 1/4 will be for diodes, 1/4 will be for FETs. So therefore, this section is a big section. 50% of the marks will be covered from that. Also, the mid-semester exam, we have to decide the format. Most probably, it's going to be online. It's obviously going to be an online. Whether it's a proctored or non-proctored, we'll let you know. Most probably, it will be a non-proctored exam. But we'll see how to do this. Probably we'll have randomized questions so that not everybody will be answering the same questions. And there will be a time limit. So it's a matter of being able to answer quickly. Okay. That's basically about what I have to say. Anything else, guys? Any questions, guys? No questions. If you don't have any questions, we can stop the class for today. And as we have been doing, you can send your questions through email or WhatsApp. I'll try to answer those as much as possible. Okay. All right. So good luck with the rest of the course and your exams.
Excuse me, sir.
Yes.
We didn't hear about that examination. There was some.
The mid-semester examination or the?
Yes, after that. Yeah.
Okay, so mid-semester examination, we don't know the format yet. Most probably, it is going to be an online proctored or non-proctored exam. Most probably, it will be a non-proctored exam, right? But that doesn't mean that you can discuss among your friends and do it. We'll try to make sure that it will not help, right? We'll try to come up with mechanisms to do that. So make sure that you are aware, you are good with the theory, right? You should be able to answer problems on your own. Okay.
Okay, sir.
There had been several messages in the chat I just saw, because they are all relating to the hearing problems, right? My microphone. Okay. Hopefully that did not affect too much. Hopefully you understood this section. And if you have still got questions, please let me know. All right. Good luck.